Here are problems 20 and 21 from your energy review. Number 20, the skateboarder in the drawing that's on your paper starts down the left side of a ramp with an initial speed of 5.4 meters per second. We are not going to worry about any kind of friction or air resistance here. What would be the height h of the highest point reached by the skateboarder on the right side of the ramp? So we're looking for how high he gets on the other side. We start with our conservation of energy equation and cross out anything that doesn't matter. Initially, we're going to say he's got no potential energy. I know he's a little bit up off the ground. We were always interested in the lowest point that we care about in the problem. And on that side of the ramp is the lowest point we care about. He does have some initial speed there, so he definitely has kinetic energy. On the right side of the ramp, he's got potential energy because he's way up higher than when he started, but at the highest point, he stops moving, so there's no kinetic energy, and there's no friction, so there's no thermal. Expanding my KE and PE, I get 1/2 mv squared equals mgh. My m's cancel, and I get 1/2 v squared equals g times h. We're solving for h, so I'm just going to divide g over to the other side, giving me this fraction, and I can plug in some numbers. 1/2 times 5.4 meters per second squared divided by 9.8 gives me a height of 1.5 meters for the skater. Number 21. A 2-kilogram rock is released from rest at a height of 20 meters. Ignore air resistance and determine the kinetic energy, gravitational potential energy, and total energy at each of the following heights, 20, 10, and 0 meters. At 20 meters, when it's first released, you first let it go. The kinetic energy is going to be 0. Why? Because I haven't had a chance to get any speed up yet. So all it's going to have is potential energy, which is mgh, 2 times 9.8 times 20, which is 392 joules of energy, for a total amount of energy of 0 plus 392 of 392 joules. 10 meters down, we can solve for the potential energy, mgh, which is 2 times 9.8 times 10, giving me a potential energy of 196 joules. You might say, well, how did you know that the kinetic energy is 196 joules? Because total energy is conserved. Look, they're all 392 joules because the energy that the rock had at the beginning has to be the energy everywhere else in the problem. So if half of this 392 was converted to potential energy, then the other half was turned to kinetic energy. So that means kinetic's got to be 196 joules. At the height of 0 meters, what's your potential energy now when it's at the ground? It's 0 because your height is 0, giving you a potential energy of 0, meaning that right as it's about to strike the ground, all of that energy, all 392 initial joules of energy, has been converted from potential to kinetic. So the kinetic energy is going to be 392, but the total remains 392 because the total energy of an object from beginning to end never, ever, ever changes.